Okay, well, I'm supposed to, yep, timer's running. My name is Aaron Wiebe. I work at BlackBerry. I'm technical manager responsible for big data platforms. I'm here to talk to you a little bit today about the software that we've built and some of the methods and interesting tidbits about how we tackle a very large ingest volume. We're up to around 600, somewhere between 600 and 700 terabytes of new content per day. So before I get into that, I want to talk a little bit about what drove us in this direction to begin with. I'm going to try and get to the technical stuff fairly quickly. In short, we have over 40 different distinct services, all of them geographically distributed, none of them with specifically well-defined logging formats or anything like that. And we used to just be taking that content, compressing it down, and storing it on filers and other traditional storage infrastructure. When we wanted to go and actually search that data and generate reports, it could take days. So the ETL pipelines were even worse. They were long, complex, fraught with failures. If one particular component died, operators would have to go in and check it out. So we needed to tackle big data. And the general idea here was we needed to significantly reduce the cost of storage, improve the access times, ad hoc, secure multi-tenant platform. We use Kerberos. We basically have a fairly well-defined user access pattern for each of the different services. You get access to a service, one service that you require access to. And we needed something that would grow with us. So this led to the creation of the LogDriver toolset. And I'm going to go through this today. This is going to be the bulk of the conversation. Our toolkit is built for loading the data, maintaining it in HDFS, and providing simple search tools. This is quite possibly the simplest piece of software that you could build for Hadoop. It includes generic Avro format for the log content, high-performance Flume replacement called Sawmill. The reason we did that is basically Sawmill and Flume feed different use cases. So, Flume is about 40% slower than Sawmill, based on the fact that it has transactional guarantees all the way through the pipeline. Sawmill intentionally doesn't. It fails predictably. And that speaks to the volume of content that we move through the system. The net result is, if you have a network failure or an HDFS failure, you can't queue up that data because you're loading it in at such a high rate. So you have to do something with it. We predictably drop it on the floor. We report on it. Now, the data lifecycle management tools are pretty important for us as well, and I'll talk about that a little bit later on. Log search and access tools, giving you the same set of access types that we had or the same types of access that you used to have for traditional log systems. So let's talk about the actual file format. The file format is intentionally built to not care about the type of data. We request basic RFC formats, and we provide mechanisms to put things back into the order we received them. Because once you actually blow this out onto HDFS, the content itself gets spread out, order is not guaranteed, so you need to actually have the metadata within the event to be able to reconstruct that. And we have obviously also support millisecond precision and making sure that even within a millisecond, we get the data in the order that it arrived. Because we're talking about 3 million, 4 million messages per second in a lot of cases. So putting them, if you're getting 200,000 messages in a millisecond, you need to be able to put it back together in the order you received it. We compress it, and we try to avoid small compression blocks. So we actually have managed in production about 87% compression with deflate. And this is there's a lot more documentation about how this is structured here, but basically we actually roll into each individual log block can be up to a second worth of content. And then you can just do more log blocks afterwards. They're numbered. So that gives you the ability to put it all back together again. There's some logic behind that we actually can guarantee that. Syslog and Sawmill ingest. We get all of the content from our services in syslog formats. And the reason for that is we've got services that get spun up really quickly. Developers put something new into production, and they say, I haven't thought at all about logging or instrumentation. I didn't do any standard formats. I just spit it out into log4j. So what we actually did is we say, OK, at least log4j can do one thing, timestamps. It's not going to be structured data beyond the timestamp that actually comes in. So we avoided the changes to the front-end services by requiring only a timestamp. The other thing about this is we actually want to make sure that the content is available for use as soon as we possibly can. When you're talking about writing data down to HDFS, you have to close the file before you can access it. So we serialize the format, and we compress it, and we drop it into HDFS. The service is responsible for only one thing, and believe me, not all of them even do that. It is providing RFC-compliant log streams, preferably over TCP. So the fact that we have services that don't even do that, syslog needs to be able to deal with badly formatted logs. So that first front step in our ingest flow takes care of that. It says, OK, you didn't provide me a proper timestamp. I'm putting the best timestamp on that log line that I can. We want it in TCP, obviously, for order. If we don't have TCP, we have even less ability to make sure that we get it in the correct order. Sawmill. So this is the actual piece of the code that we wrote, right? Sawmill accepts the content as quickly as possible. There's a queuing mechanism, a batching mechanism built into it, parses the date strings out of that, whether or not it's RFC 3336 or 5424. And we pull that out and we turn it into Java timestamps. We serialize the content into that straightforward Avro format, and we drop 1-minute files into HDFS. We close the file every minute for that particular component, for that particular service. So that, in terms of permutations, you're talking about a lot of permutations. 40 services, something like 5 or 6 components on average per service, and all of a sudden you've got 200,000 files per hour. And those files might be 2 megs, 3 megs. That's a problem. We'll talk about that in a minute. And obviously, we need to have some clear mechanisms of saying, if that content gets dropped for whatever reason, HDFS goes down, network failures, we need to be able to capture the fact that that happened. We're not necessarily going to be able to capture all of the data all of the time, but we need to know when it doesn't, we're not capturing it. HDFS has one simple job: be up. So the file system structure. When we actually deliver the content into HDFS, we have a file system structure that allows us to clearly and cleanly delineate between services, data centers, components, dates, and hours, right? So at the very least, we have a data center. We have something about a dozen data centers, and we want to have the ability for those individual file structures and the individual Hadoops for each data center. We can't transit the volume of logs we're talking about. So we want to actually make sure that that file system structure is globally unique. At some point in the future, when HDFS becomes more amazing and can span data centers, then we want to be able to merge that all back together again. These tokens within these data center service names, you can actually call them whatever you want, right? Dates and hours are the only thing that is really hard-coded. But these are the way we've approached the delineation between the services. Once the content comes in, it gets dropped into the incoming folder. So within every given application, you drop it into the incoming folder. That's where your 1-minute files spool up. And then from there, we actually have these other directories that are maintained within that structure. Working directories, archive directories, failed directories, which we don't luckily use very often, data directories. And when we actually finish all of that content delivering into the system, and it's been merged up into larger files, we flag it with a ready file so that things like Uzi can kick off and start loading in that new data set. Now, I mentioned merge jobs, and I think that's what we're about to talk about. So, OK, file maintenance. So because we've got that low delay, that 1-minute file spool, we actually have to do some locking to make sure that way we can actually interact with those files. So you deliver a log message, it gets through the pipeline in a couple of seconds, gets written down to HDFS, and a minute afterwards, you can actually use that content in your MR jobs. But small, tiny files and thousands and hundreds of thousands of them, not good for HDFS. Very, very bad for the name node. So we actually have to take that content, wrap it into much larger files for HDFS. It really, really, we've left those merge jobs off for a while, bad things happen. So this actually gets that point together where you're grouping those small files together, and by default, we wrap them into 10 gig files. So for a large component, we'll have 70, 80 gigs in 7, 8 files in this fully compressed format for a given hour. We don't want these jobs to hurt the cluster. We don't want to be spending a huge amount of time dealing with this. So we actually came up with a really unique way of taking those Avro serialized blocks and not decompressing them when we're merging them together. Now, what we actually do is it's called a sync marker in between the Avro records. And that actually is basically there's sync marker, compressed block of data, sync marker, compressed block of data. The sync markers are unique per file, per Avro file. So what we did is we said, OK, we'll take the sync marker for this, and we'll just take the block out of this file and move it straight in there. We don't have to decompress it. We don't have to deserialize it. All we're doing is moving that data set from one to another. So it's literally a map-only job that runs once an hour to take those files and groups them all back up together again. And we can't have it impacting query results. That means if I'm running a MapReduce job searching through that content as it's coming in, I can't interrupt that or pause it or anything like that in the case that I need to start merging that content. So we actually use Zookeeper to coordinate locking, making sure that when we're searching and we're merging, that data is always available. So the merge job. I already talked about this. 1-minute files into hourly files up to 10 gigs, Zookeeper for advisory locking, map-only job, and does not decompress the log content. When it's done, it sets that ready file. Right? In the filter job, so this goes to data lifecycle management, right? We've got the data that comes in. We've got this window of time where we want to keep everything, right? Every piece of instrumentation data, every little blip from all of the services. But we don't want to actually keep that for very long, right? There's an operational window in which that's useful for incidents, for whatever the case happens to be. We actually take that content after 30 days in some services, and we basically say, now we want to apply a regular expression, filter out all of the unnecessary data, and then make it available again. Again, map-only job, and you can keep all, drop all, or filter on a regular expression to actually bring that content down to something reasonable to maintain for a longer period of time. And then if there's a window, it'll delete archive data as well. So it takes care of that whole life cycle of the data that's in the system. Metadata. This is something that we just added like in the last 2 months. We have a little script that will, well, a little application that will crawl the name node infrastructure and capture details about how each individual component or service is operating. So this is actually the output of this on the command line. And this is not a very good example, but this is something from our lab, where it'll show you where how the actual trend in megabytes per hour of the ingest load is actually taking place. You can get even more detailed information out of this by digging in, same query tool. It'll give you max and minimums, averages. It'll talk about the total amount of data that you're keeping, the dates that you've kept it, and the total amount of time that you've actually got data stored for that particular service. Access tools. We built so when we approached this, it was basically the operations guy saying, well, I grep through something, it takes me 4 days. You know, you're talking about something where you're grepping to 20, 30 terabytes of data, you're pulling it off of a file or you're decompressing it, you're running it through a single core, right? So doing that, using that initial use case, we said, let's just focus on searching a whole lot faster. So we spent a considerable amount of time optimizing, writing some optimized MapReduce jobs and pig jobs to do just that type of thing. Log search is sort of the base one. It's a straight string match. It's probably the most interesting one from that perspective. We decompress the Avro block, but we don't deserialize it. We scan through, after decompressing the block, we scan through looking for that string because it's a straight byte match. If we find that string in there, then we go back and deserialize the block. But that's twice the speed of actually deserialize. Decompressing and deserializing, they both take about the same amount of time. So by not deserializing, unless we actually find a match, we increase the speed significantly. Log multi-search gives us the Boolean and or type functionality. It's a little bit easier than full regular expressions. Regular expressions, we're talking speed of government. These things are slow because everything that you pull off of disk is decompressed and blows up 10 times in memory, and then you're running it through a Java regular expression. Not happy. So we give the first tools and we say, use the first tools. If you really absolutely must use regular expressions, we've got the support for that as well. It abstracts the file system. It takes care of all the locking for you. It guarantees order on the output. And the entire idea with this is, at the end of the day, we want this to be very close to working with grep. So here's some cool tidbits of information. The merge jobs, and this is on a fairly slow cluster, or not very busy cluster. Otherwise, it would be sort of all over the place. But in short, you've got that low running, probably 200 megabits per second, 200 megabytes per second, right down on HDFS. And then you've got that spiky section there where you're actually doing a merge. The other ones are ad hoc jobs. So there's, the one at the end there spikes up to, looks to be about 9 gigabytes per second in read. But that gives you an idea of what we're working with. Our clusters range in size from, well, no, they're pretty much all the same size. They're about 12 racks of equipment each. But 100 and 200 nodes, 6 petabytes. So that's sort of where we're at right now. One of the other things that we did, sort of in the same line of optimization, was around pig jobs. So we actually use the last step in our MapReduce is around doing a sort and order to make sure that we guarantee that date order as the output, right? What we found is it's actually, there's a sort of static cost. The red circles on there are the static cost of doing a pig job in a distributed format, right? So it doesn't matter what your data input size is, it's always going to take about 2 minutes to execute that particular step of a pig job, up to 1.5 gigs of content. Up to about half a gig, it actually is cheaper in terms of time to pull that data out of HDFS and then run pig local on it. So when we're talking about a search where you're getting only a couple megabytes of response, we actually pull that content out of HDFS, run it there. And we can actually get searches down to a minute in actual real terms. A minute, 2 minutes, in that range. Okay, I've gone through this faster than I thought I would. Here's the things that we actually want to do afterwards. So we've got this infrastructure, we've got LogDriver, we've got Sawmill for ingest, we've got the merge jobs and the filter jobs, maintaining the content in HDFS, and then we've got the access tools to get into it. On the roadmap, we want to get into actually guaranteeing the input, right? So now we've got this predictable failure model where if the network fails or HDFS fails, we understand how we're dropping content, but we want to get away from that. We want to start looking at Kafka and Storm replacing Sawmill, and Kafka and Storm replacing Sawmill and Storm. We don't have and Storm yet. But that's the general idea where we've got that. If you were at the Kafka talk just across the road here, guaranteed delivery with disk caching. write that information into Kafka, pull it out using Storm, do the serialization and compression in Storm, and write it out to HDFS. That also gives us the other ability that the operations guys have been asking us for, tail. They love tail. I don't know how they expect to tail 3 million events per second, but they want to. And then adding that real-time query ability with Sawmill and Storm, Kafka and Storm, will give them that ability to go back and say, I want to tail the last 10 minutes of log content for this particular pattern, right? And there's other stuff that we could go, and other directions we could take with Storm, doing on-the-fly everything. One of the other interesting things that we're looking at is the solar cloud stuff, the Cloudera search announcement that was a couple of months ago, weeks, I don't know, something like that, and trying to integrate indexing into this pipeline so that when the content comes in, we can actually have something that is instantaneous search as opposed to 2 or 3 minutes. And we're even thinking about, what about hcatalog? What if we write metadata into hcatalog as it's coming in? We're not entirely sure if that makes sense yet, but it could. OK. We're open sourcing this. It's about 13,000 lines of code. Right now, it literally got posted about 2 hours ago. So we do have some documentation to fill onto the GitHub address. But for the most part, the code is all there. Feel free to download it, check it out, try it. If there's any interest or additions or comments or bugs or whatever you find, feel free to let us know. We're going to see if we can't keep going with this. It's a really thin layer, right? But it's specific to a large logging volume use case. If nothing else, from this talk, you might get some ideas about how we approach staging the data in, making sure that it's available quickly, and then maintaining it once it's in HDFS. OK. Acknowledgements. Will Chartrand and Matt McDowell wrote by far the majority of this toolkit. They're not here, but I wanted to make sure that they actually got the proper shout out for this. And the rest of the Hadoop teams at BlackBerry. There's quite a few of us now. The core team is only about 5 people, and operations is about 7. But there's a lot of development teams all across the organization. So, all right, questions? Yep. Can you go to the mic? Yep. All right.
Your ingestion pattern, I've seen that. I'm an instructor, so I see a lot of Hadoop deployments. I've seen that something very similar implemented like 2 or 3 times, and it seems like a very good idea. So hopefully I can have 2 questions. The first is I'd like to know if you borrowed that pattern from anywhere else, or if there's some documentation on that, or if that was strictly invented in-house. And then the other thing is, when you're doing that batching job, that compression job, have you looked at perhaps implementing like a Bloom filter or an indexing at that point, since at that point you are investing a little bit of expense in terms of processing it? So I'd like to know if you've thought about optimizing certain searches by applying a Bloom filter or an index operation at that point. So those are my 2 questions.
Yeah, so on the first one, the pattern is not terribly unique. It is a fairly standard pattern of incoming, working data type of method. I don't think we mimicked anything specific when we were looking at it, but it seemed to make the most sense. On indexing, yeah, we want to do that. The problem more than anything else is for the first initial use case, it was me and one other guy, and there's only so much we could achieve. So we're looking at it in the medium term, especially now that we've got the solar cloud stuff that's coming out. But it was a lower priority in the first pass.
Thank you.
Okay.
Could you describe your cluster hardware node? It's all about throughput, and you have a lot of load every day. So
yeah. So the clusters that we have in production range basically 12 racks, 192 data nodes, 12 disks per host, 3 terabytes per disk. We're not running into disk I/O problems in any way, shape, or form. On our production clusters, we can easily manage somewhere in the range of 50 gigabytes per second write down, and that's sort of in the terasort, teragem type testing. For the most part, what we're running into, the write rates that we're running into are about 500 to 700 megabytes per second. That includes the replication, so we're not necessarily coming anywhere close to hitting a bottleneck on write down. The trickier part, though, is because the number of name node operations for doing this, I mean, you've got a small file write, and then a file close, and then a rename, and then a bunch of moves, and so on and so forth. It ends up being somewhere in the range of 600 to 800 name node operations per second. So that can, from a lot of perspectives, put a moderate amount of load on the name node. We have not hit, the theory is that we can tap out the name node at about 3,000 to 4,000 name node operations per second, but we, even as is, the number of clients, we've got probably 200 servers writing in at the same time, and that's servicing another 2,000 or 10,000 machines coming, feeding the logging content to those. We are running into, we're looking at it and we're going, RPC, call volumes, and client loads on the name node is one of the things that we're concerned about. So, other questions? Okay, thank you. Be free.